Hello everyone, welcome to this lecture number 37 of the NPTEL course on Riemannian geometry. So last time we defined the exponential map. So this was defined on some domain sitting inside the tangent bundle, and the image was inside M. So basically, given a tangent vector in the tangent bundle, you look at we say that it belongs to this domain if the corresponding geodesic with that as the initial velocity vector, it lasts for at least a time 1, then we say that that tangent vector xi belongs to the domain, and then the exponential map was simply the value of the geodesic at 1, right. Then one can also localize at a point P and we get the exponential map at P, which is a map from a domain inside the tangent space to M at P to M itself. And then we did this, we ended the lecture with a key proposition which was the following. So let us consider the map capital phi from the domain of the exponential map to the product of the manifold. So the first component of this map is simply the projection of the tangent vector to M, and the second component is given by this exponential map. Then the key observation was that phi is actually a diffeomorphism of a neighbourhood, is a local diffeomorphism at any origin vector, at any 0 vector in the tangent space, okay. So the consequence was that if you localize at a point P, then there exists a neighbourhood up tilde of the 0 vector in the tangent space at P, such that the exponential map on up tilde is actually a diffeomorphism onto some open subset of M, okay. And note that because the exponential map evaluated at the 0 vector is P itself, this open neighbourhood will be an open neighbourhood that contains the point P, okay. So the picture was the following, that you have your manifold M, you have your point P, you have the tangent space at that point, then you have an open neighbourhood here. Sorry, maybe I should draw slightly better picture. So you have your manifold P, let me draw the tangent space here, this is 0 P. What this says is that you have a little neighbourhood here which under the exponential map is mapped diffeomorphically onto a neighbourhood of P in M, okay. Alright, so now I am going to use this map to define what are called as geodesic normal coordinates. So that is the main goal of today's lecture, of this lecture. Okay, so here is the definition. So for any point P in M, let up tilde be a open set in the tangent space containing the origin, containing the 0 vector, such that the exponential map is a diffeomorphism. Okay. We then call this set UP a geodesic normal neighbourhood, a geodesic normal neighbourhood of P in M, okay, centered at P. So the normal coordinates are a special set of coordinates defined on this UP. Okay, so what are those? So a normal coordinate chart on UP is a map which I will denote by let us say psi. I will explain what E inverse is, is a map psi from this to an open set in Rn, where psi is given as the composition of these maps, okay, where what is this map E? E is defined in the following way: I take an orthonormal basis for the tangent space to M at P, and capital E is basically the isometry from Rn to the tangent space So Rn with the usual inner product, TPM with the inner product coming from the Riemannian metric. This capital E is going to be an isometry given by the following formula. So E of u1 up to un. So you take a row vector u1 up to un and just send it to summation ui ei. Okay. Okay. So so psi is basically given by this this composition. Okay, so in picture you have the following thing happening. So you have your M, you have your tangent space at that point. By our previous thing, we have these neighbourhoods which are diffeomorphic, right. So then for your map psi, what you do is you go via the exponential map inverse and then map via this E inverse to some Rn. Okay, so then you will of course map P to the origin, but then you get this this sort of diffeomorphism from UP to some open set in Rn, which is what our map psi is, right. So psi is basically this composition. Okay, so so the corresponding set of coordinates, so whenever you have a coordinate chart, we have a corresponding set of coordinates which I will denote by x1 up to xn are called geodesic normal coordinates. Okay. So remember a while back when we were talking about the Levi-Civita connection, I said that one can always construct this a special set of coordinates so that the Christoffel symbols all vanish at a particular point, right, and we actually use this to simplify a lot of our calculations, right, of the curvature tensor and so on. It will turn out, and that will be the key proposition that I will prove in this lecture, that these geodesic normal coordinates actually also have this property that the Christoffel symbols will vanish at this center point P, and hence the name geodesic normal coordinates. The word geodesic is attached because these are normal coordinates that come from the exponential map, and the exponential map is defined using geodesics, right. Okay, so before I state this key proposition, I want to introduce some notation. So if x1 up to xn are geodesic normal coordinates, then we set r of x to be the Euclidean distance from the origin. So that is just x1 squared etc. up to xn squared and square root. Okay. And we define the following, so this is called Rp of x, because p we are fixing, so Rp of x is given by this Euclidean distance, and we also want to define a local vector field. So this is a local vector field defined on UP away from the point P. What is the definition? Del by del Rp by definition is simply xi by Rp times del I at x, right. So this is at x, and of course you, as usual, you sum over the repeated index, which is I in this case. So this is called the radial distance, and this is called the radial vector field. Okay. Later on we will see that this radial distance actually does compute the distance function that we will define depending on the metric g. It does actually compute the distance from P to a point x, right, as long as that point x is in this geodesic normal neighbourhood. Okay, but for now let me just maybe remark that by a simple calculation, if you compute the exterior derivative of this radial distance function and apply it to this radial vector field, you get 1 everywhere except of course at P, because at P your firstly your radial distance function is not even smooth at P, and your radial vector field is not even defined at P, right. But at all the other points this tells you that the exterior derivative and this radial vector field are dual to each other. Okay. Alright, so now I can state the main sort of proposition or main proposition for regarding these geodesic normal coordinates. So let x1 up to xn be geodesic normal coordinates as above, okay, on let us say UP. So I am going to use the notation from before, from above. Then we have the following points. Firstly, these are sort of centered at P, which means that xi of P is 0, and if you look at this these basis vectors that I began with, so these were, if you remember, the basis vectors for the tangent space at P, then in this coordinate system they are precisely the standard basis vectors at P for all I, right. So in particular, as a consequence of this, because my original EI formed an orthonormal basis, we get that at the point P, if you look at the metric components, that is just given by the Kronecker delta. Okay. So in other words, G restricted to this is just the Euclidean metric in these coordinates. But again, this is only at the point P, not anywhere else. So moreover, this also means that if you take a tangent vector at P, then its norm squared is just given by the Euclidean norm squared. Okay. All right, the second point is that if you take again V as above, then in fact the geodesic with the initial velocity vector as V is very simple in these coordinates. So gamma V of t is simply given by the straight line path in these normal coordinates. Okay. And the third point is that for any V as above in the tangent space at P, so of course this is as long as gamma V of t stays inside this normal coordinate neighbourhood. Away from that, you of course do not know how it looks like, because these coordinates are defined only on UP. Okay. So again, as long as this geodesic stays inside UP, you can actually compute its velocity vector. Its velocity vector up to this sort of scaling factor by the norm of V is precisely given by the radial vector field. So the reason for introducing this radial vector field is that this radial vector field exactly gives us the velocity vectors to geodesics emanating from P, from the center point P. Okay. So in particular, what this means is that the norm squared of the radial vector field is identically 1 wherever it is defined, which is on UP minus P. Okay. And finally, why are these called normal coordinates? Well, for all ijk, gamma ijk at P, the Christoffel symbols vanish. So in particular, as a consequence, if you take any of the metric components and take the derivative in the kth direction, then at P that vanishes. Okay. Alright, so this is kind of a longish proposition, let us now prove it. So let us first prove part 1. So firstly, I mean, what is xi at P? Well, that is by definition, that is the so let u1 up to un be the coordinates on Rn. Okay. So then this is of course by definition it's basically this, which is ui composed with E inverse composed with the exponential map inverse, but the exponential map maps the origin to P. So the inverse will map P to the origin, but then E is a linear map, so it will map this to the origin in Rn, but then of course the ith coordinate of the origin in Rn is 0. So each of these xi's are indeed 0. Similarly, what is by definition, what is the standard basis vector? Well, that is just the image under the inverse of psi of the standard basis vectors in Rn, right. At 0, okay. But now what is psi inverse? So that is the derivative of what is psi inverse, that is just going to be the exponential composed with E, right, and that acting on del by del ui. So which is just the derivative of the exponential map okay, the derivative at the tangent vector 0 of the derivative of the linear map E is E itself. So of E of del by del ui, but E of del by del ui is precisely these basis vectors EIP, right. And by the computation that we did last time, we saw that the derivative of the exponential map at P at the origin is precisely the identity map. So this is precisely this, okay. So that means del I at P is precisely this basis vector that I began with, okay. And then of course, because this was an orthonormal basis, this just implies that Gij of P is exactly delta Ij, okay. So that proves part 1. How about part 2? Well, by definition of the exponential map, gamma v of t is given precisely by the exponential of Tv, okay. So now I try to write this in my coordinate system. So if you want to write it in your coordinate system, you have to apply psi and see what it gives you in as an image in Rn. So this implies that psi composed with gamma v is basically just what was psi, that was E inverse composed with the exponential inverse acting on exponential map acting on Tv. So the two exponential maps cancel, so this is just E inverse of Tv, okay. But because it is a linear map, that is just T times E inverse of V. Now what is V? So V in these local in the standard basis I am assuming is given by components Vi times del I, but by the first part this is simply this. On the other hand, E inverse of this is simply the standard ith basis vector in Rn, okay. Sorry, if you that's simply the vector whose ith component is given by 1, okay, as a point in Rn. So that just means that psi of gamma v of t is simply given by t times v1 comma t times v2 etc. up to t times vn. So my geodesic in these coordinates is simply given by this straight line path. This was what was claimed in part 2. For part 3, we just note that so in these coordinates gamma v of t, as we have just remarked, is given by this straight line path. So now if you want to compute the velocity vector, that is simply given by del of t vi by del t times del by del xi, right. So you take the ith component and differentiate with respect to time. So this is just given by vi del I at gamma v of t. Okay, but on the other hand, what is the radial vector field at gamma v of t? Well, that's given by the ith component of gamma v of t divided by the radial distance times del I. Okay, but the ith component is given by t times vi, and what is the radial distance? The radial distance of this point t v1 up to t vn is obviously just given by t times norm of v, I mean t times v1 squared plus etc. up to vn squared. But v is a tangent vector at p, so the norm is the same as the norm with respect to the Euclidean norm is the same as the norm with respect to g. Okay, so this is given by t times the norm with respect to g times del I. So the t's will cancel. So if you compare it with the formula for the velocity vector of gamma v, then there is just this extra factor of norm v. So which means that if you multiply by that, gamma v dot of t is precisely given by norm v times del by del rp. Okay. Right, and then in particular if you take norms on both sides, well, this being a geodesic, right, so if you take the norms on both sides you get this, but this being a geodesic, the norm is the same as the norm of the initial vector, which is v. Okay, so dividing by norm v, we see that is identically 1. Okay. Alright, and the final thing about the Christoffel symbols, we just look at the geodesic equation. So by the geodesic equation, gamma v double dot of the kth component plus gamma ijk of gamma v of t times gamma I dot times gamma j dot, that is 0. But now your gamma v in these local coordinates is given by this linear path, right. So the second derivatives are all 0. So these are all 0. So suppose your initial velocity vector is given by vi del I, then gamma v of t by the third part or the second part is given by this, which implies that gamma v dot of I is given by vi and gamma v dot dot of k. So if you take the double derivatives, they are all 0. So then from the geodesic equation we get the following relation, that the Christoffel symbols at gamma v of t times vi vj is 0. So now just plug in t equals 0. So we get that gamma ij k at p times vi vj is equal to 0. This happens for all ijk and for all choices of the initial vector v. Right, now just take v to be the sum of these two basis vectors, right. So in other words, Vk is 0 if k is not equal to I or j and is 1 if k is equal to I or j. Okay. So, take this as your initial velocity vector, then clearly the only non-zero term here will be when right. So then this implies that gamma ijk at p is 0, and since this happens for all ijk, we get what we want. Okay. So, finally, how do you conclude that the derivatives of the metric components are 0? That just comes from the following. So, if you take del by del x k of gij, then that is just del by del x k of the inner product of del I and del j, right. But then by virtue of being a metric connection, this is the same as this plus this, but each of them are 0 since, so this is equal to 0 since all the Christoffel symbols vanish. So, this is of course at p. Okay. So, this shows that the derivatives of the metric components also all vanish. All right. So that is it for this lecture. In the next lecture, I will talk a little bit about so the next aim of our I mean where we will be headed is the following. We want to show this local minimization property of geodesics, right. So, the key tool in that will be what is called as Gauss lemma, and so I will prove the Gauss lemma in the next lecture, and then in the subsequent lecture we will prove this local minimization property of geodesics. Once that is done, we will then move on to trying to understand more global properties of geodesics. All right, so that is it for now. Thank you for your attention. I will see you in the next lecture. Thanks.